Welcome everybody. I am Nathan Wolf, aka Jitspoe, and I'm here to do a presentation about character movement physics. Do you have that tweet out, indie game lover? Hey. Helm Systems, thank you for the follow. I want to be able to retweet that, get some more eyes on it. Yeah, it's too late now. Technically, you can get through most of the game, but some of the stuff is really rough. Hey, Sam! Long time no see. Oh, I was asking if you had the tweet out yet. I was going to retweet it. Get an official tweet out there, you know. Make it look fancier. Sweet, sweet, sweet. Cool, cool. Yeah, so if everybody could go retweet that little tweet there, that'd be great. Get some more visibility on this. And let's get this rolling officially. Bam. So yeah, like I said, I'm gonna be working on character movement physics. And if I have time, I'm gonna try to whip up some quick examples on the Godot engine. I'm not sure if 1 hour is going to be enough time to do all of that, but let's get a quick rundown. For you 2 followers, hey man, two more viewers, that'd be great. So character movements, maybe a little bit smaller font in there. That is the topic for today. All right. Cool, cool. Yeah, so the plan is to do this presentation for an hour, and then we'll switch over and do some playing of demos and games that are part of the IWOCon? IWOCon, Indie World Order convention. And maybe check the convention itself out. By the way, you can grab it yourself if you would like to grab and check out the virtual convention. Walk around there, check out some cool stuff while I'm doing the presentation.
I see you creeping up on.
Or afterward, or whenever. And Koyang, thank you for the follow. Welcome. COVID-free, indeed. Infinite distance. So, the thing I want to talk about is some of the basic physics for character movement here. This is a thing that is pretty critical. If you're going to make a game, you're most likely going to make a game that has a character that moves around. Obviously, there are exceptions, but most games probably have a character that moves around. So, the first thing we need to talk about...
I'm out of here!
You traveling? All right. See you later, Sam. Thanks for swinging by. So, the first thing we need to talk about is displacements. That is sort of the key thing. The character needs to move from where it is to a new location. And that can usually be done by just setting the position plus equals some value. So if you're doing like a grid-based thing, you could do a very simple character displacement by incrementing the position of the character by 1 grid unit. But normally we're going to have some sort of velocity that is going to be the speed at which your character is moving. If it's just on one axis, velocity and speed are the same thing. But typically a game is at the very least 2D, so you're going to have an X and Y component to that velocity. If it's 3D, you're going to have X, Y, and Z. And the equation for this, if you're doing just displacement with a velocity, is going to be displacement equals V times time, or velocity times time. So you've probably seen this, or perhaps the more advanced version, which I'll mention in a moment, in like high school physics. Sometimes it's simplified to just VT because the implication of multiplication is there. Whoops, that is not the multiplication thing. So, but most programming languages, you're going to use the little star there for multiplication. So this, in a given time, will displace the character with a set velocity. And that works if you have a constant velocity. So you are, some games are like that. Your velocity is either on or off. You press a direction and your character moves at a set speed until you stop pressing that movement. That's the way a lot of kind of simple or older like platformers work. And then we have the slightly more advanced version where we take acceleration into account. And then that becomes d equals v times t plus 1/2 acceleration times t. So sometimes it'll say vi. I don't have a fancy subscript for that because you'll have your initial velocity at the beginning of the frame, and then afterward your velocity is going to increase by the acceleration. So this is how you calculate the displacement, and then your velocity is going to be the velocity plus the acceleration times time. Hopefully this is not getting too mathy. But also you can write this as v plus equals a times t, so that's a little simpler. So the displacement is how much you're going to move. Sometimes people read that as distance, like the d is the distance. That works if you're just using one axis, but displacement is actually going to be the amounts in all of the axes that you're going to move. So that is actually a vector, which can be 1 to 3 components, possibly 4 if you're doing some really crazy game, but typically 1 to 3. So yeah, that's kind of the basics on the algorithms or equations, I suppose, for doing displacement. But there's a little catch to this right here. Yeah, t is the sometimes it's done with a little delta, like delta t or dt. So t is just the time frame that you are evaluating this on. Normally it's like 1/60th of a second, but sometimes that can be variable. And this is why properly calculating the acceleration is important. So a lot of times, I'm going to say the wrong way to do things. This is something that people will often do, is they'll do the position plus equals velocity times time, and then they'll do the velocity plus equals acceleration times time. And the reason this is wrong is because the velocity is changing over that time frame. And if your frame rate is high enough, that's usually not too much of an issue. But if your frame rate is lower, or if you have a variable frame rate, it's going to change the results. And that means people with higher or lower frame rates may be able to jump higher, for example. So depending on how you do this, because sometimes there's like 2 ways you can do this and they result in different things. Sometimes people will do the velocity, increase the velocity before increasing the position, and sometimes they'll do it afterward. And this is actually incorrect, because if you imagine, let's get out some more fancy software. So if you imagine your velocity, actually let's do time over here. There's going to be time, And this is going to be the velocity. So if you do this method where you add the acceleration over time, so let's say our velocity starts out at 0, and then after 1 frame we increase our velocity by the acceleration. So we go like this, then we go like that, then we go like that, and if we have constant acceleration, that's just going to go like that. Stair step. So in reality, the velocity is continuously accelerating. And actually it's going to, yeah. So it would be like that. So our velocity is going up like that. So if we increment the velocity afterward, our distance traveled is going to be less. And if we increase the velocity beforehand, this is getting a lot more mathy than I intended. But hopefully once we start getting to some examples, it'll make more sense. So if we do it this way, actually I think I've got those backward, but either way, you can see there's a difference there. So your distance traveled is actually going to be either too much or too little. Because what we want is actually what is right in between here. I'm doing the talk right now. And hello, Luke. Doing well. And greetings, Sir Fetish Fancy.
To you, sir. That is quite a fancy fetish you have there.
So, yeah, I'm talking about the math behind character movement physics. So the thing you might have noticed is that we've got a yodeler in the chat. The thing you may have noticed is that the position offset that we want is exactly halfway in between both wrong answers. So we can actually, and I don't want to get, I could like show you all the calculus to figure that out. But what we can actually do, oops. Well, apparently did the wrong thing. I am. Yar. What we can actually do is take the velocity before. So let's call that v start equals v. And then we increase our v, our velocity. And we can take the average of those two. So rather than having to write out this whole equation, and there's some problems with that I'll get to in a moment, we can actually do the average of both of these. So this no longer is wrong. What we do is v times 0.5 plus v start times 0.5 times delta time. So that's a nice little shortcut you can do to basically have correct acceleration in your character displacements without having to do, you know, half of acceleration times, oh, you know what? I just did this wrong. This is, I'm telling you wrong information here. It's 1/2 AT squared. Yes. So disregard what I said earlier. And Kindleton, thank you for the follow. Yeah, disregard what I said earlier. This is the correct formula. But we're not even using that formula. I mean, you can use that formula. So here let me tell you about the problem with this formula. The problem with this is that a lot of times with games, you want to have a maximum velocity. Yes, forget all the wrong stuff. Just look at the correct stuff. So if you have a maximum velocity and your character is still accelerating, your velocity is going to be using the maximum value here, but you'll notice we're adding in the acceleration. So you're going to get a little extra velocity every frame, and that is not right. So the advantage to doing this, where we average the two together, actually another way you can do this, which would be faster, is add them together and then multiply by 0.5. That's one less multiplication. So you just average the two velocities together. So you have the v start and the current velocity, add them together, multiply by 0.5, multiply by your frame time, and add that to your position. So that's that is what I use. Now that I've discovered that trick, I use that all the time. It's very useful, makes it really simple, and then you don't have to worry about frame rate dependent acceleration and issues with going over your maximum velocity with this. And the other thing too is you may have multiple sources of acceleration. So you might have the acceleration from player inputs and the acceleration from gravity, and maybe you have some other forces on your character that that pull and push the character, and all of those things are acting in different ways and are off in different functions, and trying to consolidate them all so you can put it all in one function or one formula here can be really difficult. So it's a lot easier to say, all right, give me the velocity at the start, and then do stuff to, calculate accel forces, and then you'll just have this, and you can average those out. So I think it's still worth doing if you have fixed DT, and the reason for that is if you ever change that, for example, say you had a game and you started out and it was targeting 30 FPS, and then later on you realized, oh, I want this game to run smoother, I'm going to make it run at 60 FPS now, and your fixed DT goes from 1/30th of a second to 1/60th of a second, and you had your platforms and stuff all specifically designed so that you could reach a platform at a specific frame rate, and then you changed your frame rate. It's still fixed, but now you have to tweak all of your values because your frame rate changed, and then the character jump height ended up changing because of that. So maybe you can't reach the platforms you could before, or maybe it becomes too easy to reach the platforms you had before. So I think it's important to make it correct, because it can save you some grief later on down the line. So, plus it's not that much, really. Like, at the end of it, you just take the starting velocity and the end velocity and average the two together before multiplying by your delta time. Which is why I wanted to tell you guys about this trick. You don't have to worry about this equation here and try to make everything fit with that. You can just use the average of the start and in velocity. The one exception to that is if you have an impulse. So say like a jump, or something like an explosion, or any other kind of thing that happens in your game where you want to that frame set the velocity, in which case you would set the start and end. So if you had some kind of impulse, like we have impulse, then you do v equals impulse, and v start equals impulse, in order to ensure that when you do this average here, you're going to get both of these things, and you're not going to be averaging your impulse with a previous frame's value, because impulses by their very nature instantly set the character velocity, which is not a realistic thing, but it's something used all the time in video games, most frequently in jumping. Then the final thing, I think I'm going to go ahead and actually whip up some examples here before we move on to collision response. So we've gone through movement, displacement, velocity, and acceleration. And if you have a game in outer space where you don't have to worry about colliding with things, then that should be enough to get you going. Yeah, stairs are an interesting challenge. I might have some time to cover those later. There's a few different ways you can approach stairs, but they're usually done in a very kind of specific way rather than physics driven. Or sometimes people just use a ramp over stairs and then you just run up it like a slope. So let's say you're starting out on a brand new game. You got nothing. We're gonna start out with 3D scene. Let's see, demo scene. Let's call it character movement scene. We'll save that, and we're gonna add a camera so we can see what's going on here. And then we're going to add a kinematic body. Okay, that's the other thing. Now, when you're going in and you're making your game, you need to decide between a kinematic body and a rigid body. Typically, I prefer to use kinematic bodies because kinematic body is like fully code-driven physics. Like, you have complete control over what it does, and typically you don't want arbitrary things in the physics engine, like doing crazy stuff to your character. Like, you want the character to be very predictable and fully controlled, and oftentimes not exactly obeying the laws of physics. So I almost always go with a kinematic body. The exception is if you're doing some sort of physics-based game where the character moving around in wonky ways because of the physics engine is what you want. Something like Gang Beast or Goop Loop. Goop Loop I used rigid bodies because that was the whole premise of the game. This is a learn-in stream, yes.
Hey, what you got?
Hello, cheese combos.
We got the Kobe Monterey Jack, we got Parmesan Romano, mozzarella ricotta, and a chef special.
Your head hurts already?
Oh man, so many cheese combos, I can't decide.
I'm glad you like it, Fish. So, what we want to do is create a collision shape for this as well. So, there's a couple different shapes that are most frequently used for the kinematic body for character movement. I think the capsule is probably the most popular, but box shapes are also very popular. Maybe spheres here and there, but those tend to be the most popular. Sometimes they'll do like I don't know what you call it, like a pendulum shaped thing, kind of like a capsule, a pointy capsule. But I like to use box shapes myself because sometimes the capsule can do weird stuff when you hit edges and kind of cause it to bump up and do weird things. Yeah, well, it's like a cylinder with a cone on each end of it. I'm not sure what the correct term for that shape is. Or slowly slide off, yeah. So, yeah. So let's take this, make our extents about 0.5 meter wide. There we go. And we'll also throw on a simple mesh instance so we can see it. You know, it might be nice to like be able to see what we're doing here. So we're gonna do a box mesh, or cube mesh rather, and we'll set our size. Oops, 2 meters tall. Okay, so we've got a 2 meter tall by 1 meter wide box here that matches up with our collision there. And we need to add a script on here that we can control. So we're going to need some input here. Let's add a move left, and I'm going to add that to, whoops, I should probably add that to the left key. All right, left key, and we're going to add a move right to the right key. So we'll start off very simple. Have left and right movement. So, in our physics process, in Godot, we get a delta frame. This is a floating point value here. But first, we're going to do what we talked about at the very beginning. We're going to just do a simple displacement with no velocity, and then we'll move up from there. Oh, sorry. Yeah, I can do that. Let's see. Should I put it up there? I think that's gonna be out of the way for anything important. Yeah, let's see. That's going to, well, I guess people can hide behind the convention logo. Cool. Put it in the center. Yes, right here. Right where I'm typing, actually. That'd be perfect. Thanks, Hour Day Gamer. I grew it myself. Okay. So people not familiar with Godot, I'm using a scripting language called GDScript. It's built right into the engine. Pretty simple and straightforward to use, especially if you're familiar with Python. It's very similar to the Python syntax with a little hint of Pascal in there. You're welcome. So what we're going to do is check if input.action is action just pressed. So if we have action just pressed, move left, we are going to say our global transform.origin.x minus equals 1. And if we pressed right, oops, delete the wrong part there. Right. Then we'll do plus equals 1. And if I did this right, oh yeah, we need to define a starting scene, which conveniently it prompts. So now every time, well, the left worked. Did I? I misspelled it. There. That's why that didn't work. String names. They matter. Okay. So yeah. So now we've got the most basic of character movement. Character moving basically locked to a grid. So I press left and right, and the character moves left and right. One tick at a time. But unless you're doing like a board game style thing, you probably want to support velocity. So what we're going to do is we're going to add a variable called velocity, and that is going to be a vector3, start off by 0. So let's see. So we'll have, I'll just leave that there. We'll make a new physics process. I like to specify the types. The types are optional in GDScript, but if you put a colon after it, you can specify the type. Likewise there, if you put a colon and then equals, then it will infer the type from that and be like, okay, that's a vector3. So now velocity is going to be a vector3 type. You have Godot open trying to follow along? Awesome. So now we want to add a velocity. So let's create a constant. That is just going to be, actually we'll do move speed, because we'll specify the direction based on the key press. So the move speed is going to be something like 10 meters a second. A simple arbitrary number. Yeah, the colon equal is a pretty handy thing. You don't have to do it. I prefer to have all of my variables typed because A, it helps out with the auto-completion, and B, sometimes it catches bugs if you try to assign something to the wrong variable or the wrong kind of value to a variable. The script will catch it right away and be like, hey, that's not right. So now we want to check if the movement is, or if the input buttons are held down. So rather than just pressed, instead of moving every time we tap the button, we want to set the velocity based on if the input is pressed. So if input.is no, it's is action. Gosh, I can't type. Pressed. And the nice thing about GDScript being built into Godot is it like has all this autocomplete stuff. So if move left is pressed, our velocity.x is going to be equal to negative move speed. And if hey, root infection, thank you for the follow. So if move right is pressed, velocity.x, it's going to be positive move speed. And then what we're going to do is we're going to take and actually we're going to zero out the velocity at the beginning of everything so that if you let go of the button, it does not keep moving. So we're going to say global.transform.origin.x plus equals, actually we can just do the origin. I'm doing just one axis of movement here for simplicity, but for this calculation, we can do all axes. So we're going to do velocity, and we're going to multiply that by delta, so that depending on the frame time, you know, if you're running at 30 FPS or 60 FPS or 120 FPS, the amount of distance you move over a period of time is going to be consistent. I don't know if any of you have ever played some of the really, really old games from before, you know, computers had different clock speeds. Hey, Hilty!
Coming in here, say hello to me.
Yes, by the airline of your choice. Exactly. So, now, if I hold down left, I move left. If I hold down right, I move right. There's no... hang on, let me do something real quick. Okay, VSync is on. For some reason it looked like there was tearing. But yeah, so that is very simple velocity-based stuff. And you can add up, down as well. Yes, exactly, Pale Blue Zebra. I remember we had some basic games that even if you turn the turbo off, it was still too fast to play. Anybody remember Sopwith Camel? Ah, good times. But I was guilty of that too when I first started programming, you know, QBasic. I didn't know about delta and time and stuff like that. So now I'm teaching you people about that so that you don't make the same mistakes I did. Because it's super awkward if you give your game to somebody and they play it on a different computer and it's unplayable because their computer's faster than yours and everything moves super fast. Yes. So always remember the delta. All right. So that's going to be our physics process, constant velocity. Now we want to do something with acceleration. This is where this stuff comes in. So I could do a demonstration with this algorithm, but I'm probably just going to cut to the simplified one and show that so that hopefully we have some time to do some more advanced stuff. So just a reminder that this is the equation for displacement. You got your velocity times time, your initial velocity, plus half of acceleration times time squared. And then you increase your velocity by acceleration times time. Yeah, a lot of Bethesda games had issues with variable frame rate and such. So if any devs that worked on that stuff are watching, here's some tips for you. All right. So now what we want to do is calculate the acceleration. The acceleration is going to be calculated per frame, so we don't need to have a global variable for the velocity. By the way, these technically aren't global variables. These are variables within the class. GDScript is kind of convenient because you don't have to declare the class. If you create a script on something, the class is already like there. So these are basically member variables, but there's just less boilerplate code. Money monkeys. Oh, geez. Yeah, I'd heard about if you play a game at a high frame rate, like even the intro with the wagon in Skyrim just like completely freaks out because the physics are expected to run at a set frame rate. Now you can just run the physics at a set frame rate and then render at a higher frame rate, but that tends to look kind of choppy unless you do interpolation between physics frames, which starts getting a little more complicated. So, we're going to start off with our acceleration as 0. And then we're going to basically do this. We need a constant for acceleration. So let's do const acceleration. We'll also do 10. That's going to be 10 meters per second. So after a tenth of a second, we'll get up to full velocity. It can also be considered 10 meters per second squared. But I think it's easier to consider it 10 meters per second as far as thinking about it goes. So our acceleration is going to start at 0, and then if we've pressed move left, our acceleration x is going to be negative acceleration, and it's right. It's going to be positive acceleration. Now, what we're going to do is we're going to say var velocity start is velocity, and velocity plus equals acceleration, and then our global transform.origin plus equals velocity plus velocity start times 0.5. So we're basically averaging the start and current velocity times delta. It might make it simpler to break it out into a separate variable, like velocity average. So it's a little easier to read. Should probably make this script a little bit bigger so you guys can actually see what's going on. So yeah. So basically we're just taking the average of the velocity at the start and our current velocity, or velocity at start and current velocity, and then we're multiplying that. Now there's a nice way to visualize this. So coming back to this graph, if you imagine if the time steps were infinitely small, you know, our steps, the smaller you get, the smaller these steps get, up until the point where you just have a line like that. And the distance that we travel is actually, this is getting into some calculus stuff here, so don't freak out and don't worry about it if you don't understand it. Since the distance we travel, or the displacement, is the velocity times the time, if you imagine that with a constant velocity over time, it would just be the area of this rectangle here. Because the area of a rectangle is the width times the height. So in this weird way, that's kind of how calculus works. You're determining the area under a curve, and it just sort of happens that area and displacement are kind of the same thing because of math. So the problem with having these discrete steps is Like the area under this is going to be 0, and then the area under this is going to be some value. And then we've got the area under this. But that's not going to be the same as if we have the velocity continuously going up instead of in discrete steps. So if the velocity is continuously going up, it's actually going up as a line, and then we're calculating this area. So the distance that you travel happens to mathematically work out the same as the area of this triangle here. And the interesting thing about that is the area of a triangle is half of the area of a rectangle, because even though you're splitting it diagonally, it's still half. Yeah. So that is why this formula works out. We just take the average of the starts and the velocity after we've applied the acceleration, multiply it by 0.5, and then multiply that by our delta time. And then that gives us, if this is our frame right here, then we've got the appropriate distance traveled, or the appropriate displacement. Hopefully that makes sense. That's just sort of an explanation of why it works. You don't actually have to worry about that. You just say, all right, just calculate the average velocity of the start and the end, multiply that by delta, and you're good to go. So, yeah, let's see if this actually works. All this talking. Whoop, hang on. All right, let's make that acceleration a little bit less. So, as I hold the button down, this thing is accelerating, and we don't have a velocity cap right now. So, this thing just zooms and then continues on. So if you had like a spaceship type game, you could have something like this, and you just can accelerate indefinitely. And typically you'd have some sort of, hey, Jump Drive, thank you for the follow. You'd have some sort of damping or air friction or something to slow it down, so you don't just keep drifting forever. But that's kind of the basics of the acceleration. Now I'm speaking your language. Excellent. The equation of an egg on top of the box. Don't know if I have enough time to take a crack at that. So yeah, that's the basics of that. And let's see. Okay, let's talk about collision. Brain scrambled. So collision is where things get interesting. I mean, things are already pretty interesting with just this. But collision is often a challenging point. So let's say we have our character falling down at an angle, and we've got a flat line there. It died, or just a plane, That was a bad joke. So we've got our character falling down, and at some point the character is going to hit the ground, and what we want to do is redirect the character along the ground. You don't want the character to hit the ground and then just stop. You want the character to hit the ground and then slide along and keep whatever movement it had that was going horizontally. So basically what we want to do is we want to take that component of the vector, and we want to cancel out that. Now, if your ground is exactly flat and horizontal, and that's all you ever have in your game is perfectly horizontal and perfectly vertical things, you can take a nice shortcut and you can just set like the Y components equal to 0, because, you know, that's kind of what I did in my early basic days. Just, you know, you want to have the thing collide with the bottom or top of the screen or the sides, or maybe bounce, and you do like y equals like negative y, and then you have like a perfect bounce. But what happens if our character's falling down and the ground is at some arbitrary angle? We can't just set y to 0 because it's got a y component and an x component. So if our character's falling down like that, it's going to hit, and we want to move along the y component, or not the y component. We want to move along the surface parallel to that, or the vector parallel to that. So we want to take that, and we want to get rid of this. So, yeah, slopes. Uh-oh. Perfect for physics bugs. So here is where a magical thing called the dot product comes into play. So when you collide with the surface, your physics engine is going to return a normal. And the normal is basically just 90 degrees off from whatever the surface is. So, you know, if your surface is like that, it's 90 degrees, no matter what, even if it's 3D. The normal is basically the direction straight up from that surface. And if you do the dot product of your velocity, so this vector here is the velocity, and I apologize if this starts getting complicated and scrambles brains, but it's very important if you want to deal with character collision yourself. So the velocity, if you do the dot product with that, what it's going to do is it's going to give you a single floating point value. So a dot product returns, actually I should probably do a quick demonstration of what the dot product does. So our magical friend, the dot product, that's supposed to be dot, not lot product. Okay. Mouse drawings. So if you have vectors, for the simplicity's sake, we'll do vectors that are unit length, just one unit. So if we have a vector that's like this, and we have another vector that's like this, and they're both pointing exactly the same direction, the dot product is going to be 1. If we do one that's like this, and one that is 90 degrees off, it's going to be 0. Yes, mouse drawing is difficult. So in between is going to be something like, you know, if it's like this, you might have something that's like 0.9. 45 degrees is somewhere around 0.7 something. And if you want to delve into the depth of all of this stuff, the dot product is actually the cosine of the angle between these two things. So you can do some fancy shortcuts, but what we're worried about right now is the dot product is basically going to give you the amount of this vector that is in line with this vector. So if we have another example now moving out away from vectors that are just a length of 1. So if we're doing a dot product of this vector and say a vector that is a length of 2, say we have a velocity of something and we want to check how much of that velocity is in this direction, then that value is actually going to be 2. And then if it's at a different angle, you're going to get less and less of that. But it's going to give you how much of that vector is in line with this one. Yeah, vectors are fun. Yeah, lots of people will ask about the dot product. So if you're not familiar with the dot product and you don't know what's going on here, I highly advise you learn everything you can about dot products, because it is super, super useful. Like, there's so many things you can do. Like, a quick example is if you want to check if something is facing the same direction, you can just do the dot product. If it's positive, they're facing the same direction. If it's negative, they're facing the other direction. If it's 0, they're facing exactly 90 degrees. So, you can check. If the dot product is less than or equal to 0, then they're not facing the same direction. Yeah, learning game programming, actually sitting down and doing it is going to be way more valuable than, maybe not necessarily way more valuable than going through an education process, but you will likely learn more when you actually sit down and understand why things are what they are and how that helps you. So back over here. So what we're going to do is we're going to do the dot product with our velocity and the normal of the surface. So remember, the normal is perpendicular. It's 90 degrees up from the surface here. So that is going to give us how much of this vector is going along the normal. And you notice these are facing in opposite directions. So that's actually going to give us a negative value. So what it's going to do is it's going to give us the length of that. Well, sort of. It's going to give us a negative value because it's pointed the opposite direction. So it's effectively going to give us the negative length. And what we can do is we can take that value and multiply it by the normal again to get a vector, because what we want to do is we want to cancel out this vector here. So if we multiply the result of the dot product that's going to give us this length as a negative value, and we're going to, and that's one thing, sometimes physics engines will give you an invalid collision, as in you hit something moving away and you'll get a positive dot product. So sometimes you can do a quick early out check and say, is the dot product positive? Because I don't want to change any directions if that happens. Exactly. Vector is canceled. So, yeah, that is going to give us the negative. And what we need to do is multiply that value times the normal. So if we do, we'll do the dot of the velocity and the normal. And then what we want to do is multiply that times the normal. And then we'll get this vector. So we can just take and subtract that vector out of our velocity. And then we've just got the resulting vector, which is going to be the vector that is along this surface. So we hit this, we cancel out anything that's going down into it, and then basically project it. And a lot of game engines will have like helper functions for projecting, so you don't have to write all of that out and calculate it manually. But it's good to have an understanding of how to do that, especially if you're writing your own game engine from scratch or doing something in an engine that doesn't provide all of that stuff for you. So hopefully that is helpful. Oh, and one thing you can do, say you want to have it bounce instead of just slide, you can actually subtract. So once we have this vector, we can subtract the vector just by itself, and that's going to have a completely inelastic collision. So you'll hit the angle, and then you'll slide down parallel to the angle. But if you wanted to, say, bounce off of it, you could subtract. If you did 2 times that vector, if you subtracted 2 times that vector, then you basically have this. So your character would go down here and bounce out. And if you did 1.5 times that vector, then you'd have like a 50% bounce. And you could use any value in between there. So yeah, hopefully, I mean, this is about the time that I had for the presentation side of this thing. Tack a curve on there to make it interesting. Hopefully that was understandable, I guess, and informative, maybe even entertaining. But that's down a Bezier curve. Hey,
100 bits?
Thank you so much for the
I'd buy
bits.
that for $1. Ha!
Yeah, so if you have a curve, basically what you just have to do is get the normal on that particular part of the curve. Hey, Stinklewinks. There's not going to be like an exact. I mean, the only thing you can do is just have smaller and smaller step increments to be more exact on that. And maybe there is a way to be exact. I don't know. It starts getting really complicated, but you can get the normal on any one particular point of the curve, basically where you have your collision. So if your character hits this, if you're using curves to, say, define terrains or something in your game, then hopefully you've got a way to get the normal off that curve when you collide with it. If you don't have a way to get the normal off the curve, what you can do is you can take 2 points of the curve that are like right next to each other, and then you can get the vector between those, and then basically 90 degrees off of that would be your normal, and then you can do these calculations with that. A curve for your multiplier on the dot product. I see. I mean, the bounce is going to happen as an impulse, so you wouldn't really be able to put a curve on that, so to speak. But what you could do, if you wanted to have, things animate a little more, is when you have a collision, you could do a bit of a curve on the displacement, so you have maybe some squash and stretch or other things. But I would leave that as purely a visual thing. So you do your bounce, and then maybe just transform the mesh itself to do a little squash and stretch. But yeah, any questions on this? There's a lot to cover in a short period of time, but hopefully you guys have a better understanding of how to do physics calculations for character movement. One other thing I should note on here is that when you have a collision, you should have multiple update steps in your character. So say you have your character here and it moves down and it collides, and so this is the original movement that it would have. Like, it would go through here, it should move this distance, but you had a collision partway through. So usually when you have a collision, it's going to return the position of the collision, the normal of the collision, and the amount of travel distance and or the remainder. Sometimes those are floating point values, as like a percent of the distance or a vector. Kind of depends on the engine. So in Godot, they return vectors for the distance that it traveled and the remainder of travel left. And then what you want to do is you want to continue the movement parallel. So you'd start out, you'd have your collision, maybe that's like halfway through, and then you'd take the percentage of the distance you traveled, and then you would do another update with what's left. So say you traveled, let's just say 0.3 or 30% of the distance, and then you want to do another update in the same frame, doing whatever's remaining, like 0.7. So you have your collision. Basically what I do is I just have a while loop, and I have like a threshold on there, so it does like 3 to 5 updates. If you've had more than 5 collisions in one frame, you're probably stuck in something and don't need to worry about it. So at least two to 5 updates. So I just put my character movement in a loop and basically decrement the delta by, or scale it down to whatever the remaining portion is. It can start getting kind of complicated, but it ensures that you don't have erratic movement when you're moving along the ground, because sometimes you'll get arbitrary collisions and your character will kind of like stutter as it's moving. And it's good to have the character move a consistent distance every frame. So if you're touching the ground, and the other thing this allows you to do is calculate because a lot of times what people will do is they'll just cancel out the gravity acceleration component when you're on the ground, which can result in weird things. Like if you're going down a slope, you either need to project the velocity down the slope, or your character is going to like go out, fall down, go out, fall down, go out, fall down, and you have like this kind of stair-steppy movement. So what you can do is have the acceleration always pulling down on the character, and then some frames, if they're on the ground, they're going to immediately hit the ground again, but then you just redirect the velocity along the slope. So that has the advantage of, if you want to have mechanics where the character slides down slopes and gains velocity, you can do that. Fist of the Forgotten. Or, just other things like that. Makes the movement feel more natural. Sometimes you got to cheat some things, like if you're going up a hill, maybe you don't want the gravity pulling them down. So it starts getting into a lot of tweaks and feel and stuff like that, which I didn't really have time to get into today. What if the geometry is like 2 parallel quads and you slide in them from the side? Yeah, so that's why there is a limit for how many times I do the loop. So you're saying, like, if you had a scenario like this, where the character, like, slid in between those things. Ideally, you want to avoid scenarios like that, where you've got two things that are the